So come for the Facebook, stay for the GE, I guess. Thanks very much for the introduction, and very much a big thanks to the organizers for the invitation to speak. GE is a 125-year-old company. In case you didn't know, it's the last remaining company on the Dow, the original Dow. And it has gotten there in part because it's famous for reinventing itself. So for instance, that electronics arm that you might know about, you may have some of this in your house, is no longer part of the GE portfolio. The biggest transformation that they're undergoing is the digital transformation from analog to digital. And what's exciting as somebody coming into this company fairly recently is that this is the company that makes the machines that powers all of our lives. And the way to think about it and the way to explain it to your friends is if it spins and your life probably depends upon it at some point, like an airplane that you flew in or some sort of power system, it's probably made by GE. Today's talk isn't about GE per se, but what we do with the data that's produced by heavy industrial equipment. And what I really want to focus on, obviously, is the machine learning that's done on that data. I hope it stimulates an interest, and I see this as a tremendous white space and a whole bunch of really interesting opportunities for the young people in the room to get into. So what's the agenda? Very briefly, I'll give a background on myself, a little bit on GE and the industrial Internet of Things, talk about this industrial machine learning set of challenges, and again, try to frame those as opportunities. In particular, in drawing distinctions as starkly as I can between the consumer internet and consumer products, I'll talk about optimization metrics and how those might be different in the industrial internet. Talk about the marriage of physics and data-driven models. Talk about the need for interpretability in a heavily regulated environment, and last, touch upon privacy and security. So very briefly about myself, as you heard in the introduction, I started Wise.io about 5 years ago. We built applications for customer support. Think of what we built on the hood as sort of an end-to-end model for doing building and serving predictions at scale in a multi-tenant environment, sort of like TFX. But we did this with a very verticalized focus, so our focus around products became very important. I also teach at UC Berkeley, and while I love teaching astronomy, I actually fell in love with teaching Python and Python for data science, and got involved and became the co-founder of the Berkeley Institute for Data Science a number of years ago. Most of my papers that I've written academically, while some of the more recent ones have been around machine learning, mostly been around time series and doing inference on large amounts of time series data and images. And you can imagine that's why somebody like me would fall into ML, is because we had a big data problem a decade ago where we're producing more and more images from telescopes, and we needed to do real-time discovery from that. And my colleagues at the time were basically saying, well, you'll just hire more grad students to look at the data. And I said, no, experts don't scale like that. So why did we come to GE? It's in part because we're coming a little bit back home to our roots as physicists and astrophysicists, but in part because we're really drawn to the data. Like many of you are drawn to other large companies with large amounts of data. So we think about this industrial Internet of Things, or IIoT, as the internet of really, really important things. Not Fitbits and thermostats, but things that really matter in your lives. And the amount of data that's being collected already is starting to rival all of the data being collected around and by people. It's projected to get to something like 600 zettabytes by 2020 per year. And if you just do the math, right, on the total amount of data that can be produced by people, think about what you produce, about 1 byte a second if you're typing or you're talking in sort of a Shannon information sense. Call it, max number of people ever on the Earth will be, 10 billion. So then there's pi times 10 to the 7 seconds per year. And if you do that math, you get to the max number of bits or bytes that could ever be produced by all humanity of something like 200 petabytes per year. And we're nowhere near that right now, and that's amortized over 24 hours, assuming that you type like this. We're nowhere near that, but what's clear is that the data that's being produced by these machines is going to very quickly outswamp all the data produced by people. So just to give you another example, a jet engine, which GE makes, produces about 1 terabyte of data per 5-hour flight run, which is of order sort of a Twitter amount of day. And there's about 50,000 jet engines flying per day. So the amount of data is just mind-boggling. Obviously, then the next question is, where does machine learning come into this? And the answer is in a couple of places. So one, obviously, is in preventative maintenance, which is asking the question, when in the future is it optimal to take a part offline and potentially fix it? Then there's sort of failure anomaly detection in sort of a real-time enough way, detecting faults that could have catastrophic consequences if not dealt with immediately. Assistive diagnosis and treatment. This is providing sort of augmentative help for clinicians, analysts, et cetera, to accelerate their analysis of the data. And then systems optimization. Think about trying to get the most amount of power out of an entire wind farm. So obviously that has implications for how we think about the various different metrics. But before I do that, again, just to try to draw this distinction, on the left-hand side, I'll show you kind of true positive, false positive, et cetera, for the consumer internet, and then and the implications thereon. And then on the right-hand side for the industrial internet. So if you have a true positive, in the consumer internet, you've made a good, movie recommendation in your site. If you've got a true negative, then you're not shown an ad that potentially you would have hated. In the industrial internet, a true positive means, identifying a cancerous tumor early using a CAT scan or MRI. A true negative means that you avoid taking a jet engine off a plane to fix it when it doesn't need to get fixed, causing about $200,000 of disruption, and obviously you getting pulled off the tarmac and getting mad at your airline. That seems like a big deal. On the consumer internet, if you make mistakes, on the top left, the false positive is you got a box of clothes in your subscription service that you don't like and you're really mad. And then, false negative is, you're really mad because you got spam in your inbox. It was misclassified and was put in your inbox. In the industrial internet, you're taking a megawatt power system offline and potentially knocking out, thousands of people's lives for several hours. And if you get it wrong in a false negative sense, you miss detection of a crack in an oil and gas pipeline that winds up blowing up and killing people. So, the left-hand side is meh. The right-hand side is, really a really big deal. And I know I'm being sort of semi-facetious here, but I am trying to draw that distinction for you about the societal impact of doing something right or wrong on the left-hand side versus doing it right or wrong on the right-hand side. So interestingly, this leads to some really interesting problems and considerations in optimization. It gives us sort of an impetus or a rationalization for imbuing bias into our optimization metrics. On the left-hand side, you can see a very famous plot showing the correctness of the prediction of whether it's going to rain or not in your hometown. And you can see that some of the various different predictions are actually biased in the sense that they're telling you it's going to rain more often than it actually does, and some are actually pretty good. So you might determine, if this is the thing that mattered for you, that being on that sort of curve of slope 1 is the right place to be. But it turns out that having higher accuracy is not always the most important thing, right? Sometimes you really need to minimize your false negatives. And so here you might introduce a bias into your metric to say, no, I'm going to choose a curve that's farther off to the left because I don't want to ever get rained on. Another way to put that, this is something articulated by my colleague June Andrews, who Cornell math PhD, who just joined us from Pinterest. She basically put in these fairly stark terms that if you have this optimization metric around false positives, false negatives, et cetera, and you have these cost numbers that you really care about, there are some industrial internet applications where the cost of a false negative basically is astronomical. I'm an astronomer, so I won't use that term. It's very, very large compared to the other ones, and this epsilon term, the cost of a true negative, is very, very small. And so this has some interesting implications for how you even do this training, because in that curve on the left-hand side with your false negative, if you have very few training examples, then it means you need to model exactly where you make your cut, not in the optimal place where you see the vertical line there, but much further to the left, because you don't want to ever have any false negatives in reality. And so one of the things that we're working on is fitting that sort of noisy false negative tail with some other sort of more normal distributions, and using that as a way to sort of model out where our lower bound needs to be in making our cuts. Another thing that is different between the industrial Internet of Things and what we have in the consumer world is that, unlike in human interactions and interpreting, all the biases that come from those interactions, there actually is a ground truth in the industrial Internet. Margaret Mitchell yesterday talked about the challenges and really the lack of ground truth in understanding nebulous things like motivation and interest of people. But in the industrial world, there's actual physics happening, right? And so there is an actual temperature of that part. And whether you measure that well, or whether your sensor is noisy or it's gone offline, or whether you have enough sensors or not, there is a physical grounding to the manifestation of what it is that this thing actually does. And that can be a very simple system, like at the top, or it can be a very complex system, like at the bottom. I find it very satisfying to know that there actually is a reality of what it is that you're trying to do an ML model on top of. But what's interesting is that because these are physical systems, I think in some sense this held back companies like ourselves and this sort of larger physical universe, in that they didn't have to be all that data driven. If you think you know, or you believe you know enough of the physics of a system, then when you have data coming in, you can model it with the physics that you think is important and then make predictions based on that. So there's some great things, obviously, about physical models of these systems. We can capture, an a priori understanding of the system without really any data, which is pretty amazing. Simulate, and anticipate futures that haven't happened yet. So there could be a failure mode which literally has never happened, but you could see what happens when you throw a bird into a jet engine and actually make some simulations of what could actually manifest in the real world. And the very nice thing, and this was something that was discussed by Bin Yu this morning in her keynote, is that the parameters of those models are very interpretable, right? This is almost the definition of being interpretable if there's a physical meaning to those parameters. Now, in contrast, obviously, physical models don't learn very well from new data. And this is the next one here, I think very importantly, points out that we don't know all the physics, especially of these complex systems, right? Unless you're modeling, a mass spring system, anything else beyond that is going to be an incomplete representation in your, supercomputer simulation or in some sort of finite element analysis of that actual device, right? And that will mean that you won't get the predictions exactly as they actually will manifest. It's very hard to refine these models. So if you make a mistake, oftentimes this is somebody with deep domain knowledge who has a PhD in that particular type of metallurgy has to go in and actually jigger the model and produce new versions of it. And it's also very difficult in some sense to incorporate non-physical metadata. So if you want to see why this thing failed, you could go back, obviously, and realize that it's the same operator the day before that's like, turning the dials up and down. How do you put that into a physical model, right? In contrast, in the sort of data-driven world, obviously, you don't need a physical explanation. You just let the data tell you. It naturally improves with more data and outcomes. It's extensible when you add more data sources. That's pretty easy. But you often require previous exemplars. So if you're trying to model something that's a very, very long tail, a failure mode that really hasn't been seen yet, almost by definition, you can't model that. You might be able to recognize those modes as being not seen before, but it'd be very hard to understand it. It's uncertain how to generalize these, as you all know, and they tend to be very black boxy. So deriving intuition from these data-driven models is very hard. Now, one of the things that we're excited about now working at GE is marrying the physics-based models to data-driven models in this industrial context. In some ways, I think about the physical models, if done right, get you sort of 80% of the way there, and then the data-driven models, if sort of attached to those, can actually get you, the rest of the way. So, in some sense, the traditional featurization that we all did, before deep learning became a big thing, of taking raw data, featurizing it, that was capturing our domain understanding, that was capturing our physical understanding of these systems. So we already were kind of imbuing physics into these models. And obviously in the reinforcement learning world, it's these AI gyms and other types of simulations that then allow you to train in an offline way in a simulated environment, put that into a real environment, and update your model with actual data on the ground. And what you see there is a plot from a drone simulation from AirSim, I think that's the Shaw paper, showing that the X or the Y location as a function of time for doing a specific maneuver is not too far off from the reality in the simulation. And what you'd hope is that you can build a system that can actually learn and update itself using the physics model, then going into the data-driven model. Another thing you can do, obviously, is impart or imbue or actually impose physics into your model itself. And there's a couple of great examples of this for those that don't know. In computer vision, you can impose geometry like this rotational invariance, and you can put that into specific layers of a network. And a recent paper by some folks at NYU have basically imbued quantum physics into recurrent neural nets. So they used essentially what they call a recursive neural net. So it sort of derives from some language modeling. And what they did is they basically imposed that all the interactions that they were looking at in the particle physics accelerators had to obey certain physical laws like conservation of momentum or conservation of energy. And that allows the model itself to explore a much more narrow set of parameter space where all the laws of physics that we know about are not violated. And then there's sort of a last component or last approach, one that I want to spend a little bit of time on, which is modeling residuals of the physical models. And so what do I mean by that? This is a bit of a toy model. Say you've got observations, say a sensor has a temperature that has some regular patterns in it. And given all the other sensor data around it, given the history, you might be able to build a test data set that shows that you do pretty well in measuring that quantity, but if you look at the residuals from that physical model, you see that there's still some obvious structure that's missed. So this is an example where you think you've got all the physics, but you know you don't, and so now you need to do something with that. So what you can then do is take categorical variables, take other time series, take who was the operator the day before, whatever other data you want to throw into that, and instead of fitting the original data, all you're doing is then fitting the residuals. And if you build a domain-driven and data-driven model for those residuals, you can actually do quite well. So I think there's a lot of traction here, and in these physical systems where we have an incomplete understanding, I think we're going to be able to make some good headway on that. Okay, another, I think, interesting distinction here, although it does bear some resemblance to some of the things that have been talked about at this conference, is that industrial machine learning applications still need to be understood. And what you see is a stark reminder from the person that was operating the Deepwater Horizon rig that there was lots of data, and there were even actions that were being suggested to this operator of how to bring things back from the brink. And the operator said there was just too much data, I didn't really understand it, so and that's a big deal in the industrial Internet of Things. And obviously the way to deal with that is just sort of trade off some accuracy and basically say, I'm willing to give up on some of these very accurate algorithms just in the spirit of getting more interpretability, so that when I present these results to humans, there'll be a resonance with that. So I know I'm pissing off the entire audience because each one of you has your favorite algorithm and you want to have yours like a little bit higher or lower. This is totally unscientific. But what I will say is that some of the early R&D work that we did, which served us very well in our applications, was not just using sort of model level importances in decision forests, but coming up with a rigorous framework for coming up with something we call instance level feature importances, which gives you a very nice way of explaining why you got a prediction you got out of decision forests because of the specific data for that specific instance. So essentially creating reason codes. And I think the work on interpretability is still very much an open question, but very clearly, for the people which are ultimately the recipient of a lot of the machine learning that we do at GE, is not just surfacing, the what should you do, but the why did we say you should do that, so that you build up this notion of trust. And so if you're telling somebody, we think you should take this engine offline, or you shouldn't take this engine offline, we should give them very clear, summarized reasons why it's looking like this is a problem. Or if it's not a problem, say, look, there's a couple things you might want to look at, but we still make the prediction that it's okay to keep it running. And so this is just sort of a toy example of what that might look like for that end analyst. The other thing that's important, of course, is in sort of the full stack view of building ML systems, which is universally required across not just the consumer internet, but also industrial internet, we also have to capture feedback, right? So when an analyst looks at this image and clicks on something, we need to know that they're clicking on it. We need to engineer that directly into the applications that we build so that we can allow these systems to continually learn and get better and help people more. There's also sort of the regulatory imperative around interpretability. You heard about this morning about this European law, which goes into effect in the beginning of 2018, which means that in decisions that are made about you using algorithms, people are going to have the right, if you live in Europe, to understand what was the data that drove that decision, which is remarkable if you think about the requirements around that. And it's not talked about enough that this is, in some sense, the regulators getting ahead of the science. But in the industrial machine learning world, we already have massive amounts of regulations around, you name your body, right? So the FAA, the FDA, the NRC, et cetera. And what they wind up doing is effectively blessing specific algorithms that can then go into, say, a medical device. And what's interesting is that they bless not just the algorithm, but the model that the algorithm creates. As far as I know, there's really no legal standing or even contemplation of the idea that you could have continual learning, that you could have a model which knows how to update itself with more data. We need to figure out a way to explain that and to actually drive potentially regulation that allows us to deploy these models into the real world. And that means from a computer science perspective, we really need to have an understanding of how we provide stability guarantees. Getting back to Professor Yu's talk this morning. If we can provide stability guarantees given updates in the model and the data, then I think we have a shot of being able to deploy these models, which we all know are going to wind up getting better as they get more data. And so last, there's also this question around privacy and security. It's no secret that nation states, bad actor nation states around the world, are trying to get at some of the most important physical systems like nuclear power plants, and try to get into the control systems, learn about them, and potentially even do havoc. So the easiest thing to do is just block that whole thing off from the outside world. But what we really want to be able to do is build ML models, if we're doing systems optimization, to improve the functioning of these power plants. And we want to do it not just on one power plant, we want to do it on multiple power plants. And so how we share data from these very heavily regulated and very secure environments for the benefit of producing better models across these different data sets, even with potential adversaries who don't even want to talk to each other, and produce those models to serve everybody and do those better, is a really interesting problem. And there's some interesting paths towards this. There's a new paper that came out of the medical world on using differentially private GANs to act as a surrogate for data sharing. So instead of me handing you a very private data set, build a GAN on that data set, and then hand somebody the generative part of that, and they can provably produce and actually run then other types of models on top of this data, which has nothing to do and is provably not something you could tie an individual back to, but then they can actually use it and potentially build models off of that that have some real value. And then there's obviously the whole sort of computation on encrypted data and doing actual computation in hardware enclaves. And there's a couple of references that I have there. And then last is sort of the privacy-preserving deep learning ideas that have come out in the last several years that allows you potentially to be able to send back only a subset of the updates that you might have in a given epoch, where each actor, which wouldn't even have to see the data from all the other actors, could send their updates to a central system, which could then propagate the better models out to all of them. We're working on things like that. This is just a couple of highlights of the things that we're doing within the WISE team at GE. And one of the things that I think you wind up realizing when you get to work in a white space with all the low-hanging fruit that we have with the data and the sorts of questions that we have is that there are a lot of problems that don't seem to be addressed that seem fairly fundamental in the consumer world. And because we have constraints that potentially others don't, we wind up having to do some R&D around that. So I won't go into the details of those, but I did want to say that we also recognize that connections to the academic world are important. And GE is a founding sponsor of the RISE Lab, which is the successor to the AMP Lab. And I've noted here a couple of different projects that we're particularly excited about around doing distributed computation in the context of machine learning and doing it in a privacy-preserving way as well. We're also a member of the Stanford Data Science Initiative and very excited about a new project from Matej Zachariah and his cohort on this thing called WELD. What I'll do here is just end with something that I think you all know, but I like to kind of remind myself of this and many audiences of this, that machine learning is fundamentally a systems problem, and putting it into production has very little to do with algorithms. And if you haven't read this paper by D. Scully and colleagues at Google, I highly encourage it. The only real test data that is data that hasn't been created yet, right? And because it hasn't been created yet, you can't actually test it offline. So the only real way to do things is to put things in production and hope that you've built enough guardrails into all the different parts of your system to make sure that you're not doing something catastrophic. And if you think about the different levels at which you have to consider what it is that you're actually optimizing, it's kind of mind-blowing. A lot of times we focus on that top one, on the algorithms and the models. But then if you start thinking about instantiating those in software and hardware, you get into some interesting other problems. And then if you start getting it into the sort of, team level, there's some other interesting questions about, opportunity costs and why are you spending more time on this versus that, because this other one might have a higher business value. And then go farther and farther out, and you wind up realizing in some sense that the goal of, I think, everything that we have to do in the industrial internet and also the consumer internet is to tie all these different levels essentially to a business outcome. And yes, you can usually tie, a false positive rate to a certain number of dollars if you're lucky, but oftentimes we don't think about optimization over the whole company or the whole team. And once we start thinking about that, I think we're going to be in very good shape. So what I'll end with here is a slide I think that keeps me very excited about the work that we get to do at GE, which is just if we do machine learning right, if we get 1% improvements in efficiency in any one of these fields, these are sort of the dollars that we're talking about. It's in the tens of billions a year for just any one of the subjects and domains that we get to work on. I think of the data that we work with as touching the lives of ourselves, not as consumers, but as people. And I think of what GE does and those in its cohort as powering the world and doing the things that actually moves us. So with that, I'll end and very happy to take questions.